Okay, let's finish the parameterization. Basically getting a parametric representation of a curve in 3D space. And then we'll get on to the new topic, which is a vector function. So in the previous lecture, I have basically talked about essentially how to obtain a parameterization of a curve. The typical description of a curve are in a format such as x squared plus y squared equal to a squared. That's a typical representation of a curve equation, like this is a circle, of course. You can have y equal to x squared. Okay. Or you could have two planes together, a1x plus b1y plus c1z equal to d1 and two planes together give you a line. Right? Because now the idea is we want to obtain a different type of representation, which is what we call the parametric representation, or here we say just parameterize these equations into a set of parametric equation here. So for planes, we can have really there are infinite number of solutions. For circles, you can have x equal to a times cosine t and y equal to a times sine t, very typical way of representing it. And here this one you can have x equal to t and y equal to t squared. And this one really depends on the plane. You can basically still derive a set of equation which is x of t equal to something, and y of t equal to something, and the z of t equal to something, right? Depends on the given two planes. Yeah. Oops, there you go. So that's the objective. So given a circle, given a certain curve, you need to be able to obtain its parametric representation. The parametric representation, as I mentioned, it also describes, basically give a physical meaning, it describes a certain type of motion, a point or particle that is moving along that trajectory. And in the last lecture we have demonstrated, right? If I have a circle, the circle itself has nothing special, it's just a circle, right? But if you relate this parametric equation, when you put in a different type of t into this parametric equation, and then you will see it becomes a moving particle along the circle now. Right? That's the idea. Relate the parametric equation to a certain type of motion here. If I change this coefficient of the t to different ones, instead of 1 here to 2 or 3, then there will be different speed. If I change the signs, and it will change to basically moving directions, right? And so that's the idea here. Even this x equal to t, y equal to t squared for y equal to x squared here, this one here, this is a parabola curve. Okay, there's nothing strange about it. But when we put it into a parametric equation, it becomes actually a certain type of motion now. If I plot t here when t equal to 0, and initially this basically means start at 0, 0, right? If I put a t equal to 1, meaning it goes to 1, 1 at t equal to 1. So that gives you an idea, this particle is moving, right, in this direction at here. So that's the relationship between parametric equation. Now, parametric equation is not unique. Like for this one here, I can certainly rederive this one to describe a different type of motion. Right? So for example, maybe what you really want is, can I get a particle, a motion particle, let's say starting from here, right, and then going back to 0, 0. So let's say you started here, going back to here, and it's going along this y equal to x squared curve. Then how do I derive a parametric equation to describe that type of direction? Right, that's Then you come back to here and say, okay, basically means at t equal to 0, where is this point? The point is at 1, 1, right? That's the coordinates. And when t equal to 1, let's see, and you're at 0, 0 here. Okay, suppose that's the type of motion we're looking for. Then when t equal to 0, so then you strive to get a certain answer here now. When t equal to 0 is 1, 1. When t equal to 1 is 0, 0. So maybe I could let x equal to, let's say 1 minus t. And then y equal to basically 1 minus t squared. Right, so substitute t equal to 0 here, you get a 1. And same thing, you get a 1 here for the y. When you substitute the t into this one here, you get a 0 and 0 here, which is exactly this point. So that's the idea. You still get a parametric equation. You see these two here, they are different. Right? They're different. And they actually describe. They all basically describe this curve, but they describe a different type of motion now, right? Okay. So that's what I want you to establish. The idea is, so in the next few lectures, we're going to learn scalar integrals, and in the future we're also going to learn vector line integrals. We'll basically do integrations over a curve in 3D space, and we need the parametric equation for that curve. And the curve often is given initially like this, giving a label initially at here and ends over there. So we need to get an appropriate parametric representation of the curve. So I have two more examples, okay, to give you for parameterizing the curve. So this one in here, this is actually part of one of the midterm questions some years ago, and it gives you 3 points. Okay, one is origin, another is 1, 1, 0, and the last one is 1, 1, 1. So giving you 3 points here, and then we can establish two segments of curves. So this is a C1 and this is a C2. Okay, and the idea is to obtain a parametric equation for C1 and C2. C1, C2, essentially there are two straight lines. And I don't want you to derive like a straight line equation like you did in the previous lectures here. And here, mostly purely based on observation or purely based on even your high school function concept, you'll be able to get the parametric equation here, okay? Yeah. First of all, let's look at the C1 here. So C1 is the straight line between origin and the P, which is 1, 1, 0, meaning C1 is inside the xy plane. If it's inside the xy plane, so parametric equation you're looking for basically means, let's say for C1, we're looking for what is x over t, what is y over t, and what is the z over t. Okay, so that's the idea. And then now you can, based on my description, if C1 is within xy plane, then the z over t, doesn't matter what t value, the z over t is going to be always what? 0, right? So that's easy, so that you put it down, 0. Because x of t, y of t, z of t essentially represent the coordinates for any point on the C1. And then for x of t, y of t, if I look at this segment here, if I look at in the plane here, when you connect 0, 0 to 1, 1, you basically get a 45-degree line here, which is y equal to x. Right? So if y equal to x, according to the examples I'm giving in here, y is a function of x. The simplest way to parameterize the curve is to let x equal to t, and then y is whatever the function is. Okay? So then here I could just say x equal to t and y equal to t. And that's the simplest way to parameterize it. But you don't stop at it here, okay? Because in this particular case, your curve C1 is specifically just a segment of a C1. Okay, it's only between 0, 0 and 1, 1, 0 here. So your t has to be given a range to represent the curve C1. Then in this particular case, your t definitely start from, you can see, you can write it as t is between 0 and what? 1. Because when t equal to 1, you're at 1, 1, 0 here. So that'll be the range for the t. Because this is crucial in the future when we learn line integrals. You need this range of the t as your integration limit. Okay, so we're going to come to that very quickly. So that's what you really need to put it down beside this parametric representation here. Now, before we get to C2, can I ask you a quick question at here? Can you give me a different set of parametric equation for the same C1? So, not different from this. Okay. Think about it. T squared and t squared, okay. That's true, right? That's true. But I think this is a little bit complicated than this now, right? So if I think along the same line as this, 1 minus t. Okay, so if I use 1 minus t, then what will be the t's range? From 0 to 1. Okay, it's still, you mean still 0 to 1, right? Would that work? If I plug in 0 here, initially your x of t is actually at 1, 1. And then this is when plug is 1 here, and it's 0, 0. So what's the difference? That's a really good point here. What's the difference between these two at here? For the first one, the direction goes from where to where? Here, right? And the second one goes from this direction here. Okay? Yeah. That's good. Yeah, both are correct. Okay, both are correct. Now sometimes the question will specifically give you the label here, the direction. Okay, sometimes the assignments will give you the direction. If the direction is given, then this one, if the direction is given like this, then this one wouldn't be the right representation. But here, this is fine, right? Any other suggestions? So if I still use a t and a t, but if I wanted to travel a little bit faster here, what could I do? I can, instead of a t, I could also use what? Let's say 2t. Okay? Now if I use a 2t, then what will be the range for the t now? Excellent, right? 0 to 1 over 2. Okay. So you can literally see, you take 1 second to travel, here it takes 1.5 second to travel. Okay. So that's the point, you know, when you derive parametric equation, it's not unique. And actually what you really want, if it's not unique, then you want to actually use the simplest form of parametric equation. Because, you know, parametric equation, you use it for integration. Let's say if you use a t square as somebody suggested, which is nothing wrong with it, but then you actually will complicate the integration following the parametric equation here. Okay. Yeah. Good. So that's C1. So let's take a look at the C2 at here. Look at the C2. So what's the nature of the C2 here? C2, let's say I'll draw an arrow here. Let's say moving from P to Q. Okay, moving from P to Q. Basically, it's moving vertically, right, from P to Q, and the X, Y, Z goes from 110 to 111. So now your x, y coordinates, if you look at anywhere along this PQ line here, what is the x coordinate value? What is the y coordinates value? 0, 1, and 1. Okay, that's a very common mistake. Because when you're going along here, the xy value, you look at the xy value here, they're not changing. Okay, they're being kept as constant, which is 1 and 1 and here. So you can just simply write down 1, 1. However, the z value goes from 0 to 1. So that's a changing quantity. Then this is where you can have a little bit differences now between different people. So you can simply use just a t, meaning you want t go from 0 to 1. Right, that's how you describe the motion. Or somebody use a 2t. Right, so that's basically up to individual now. But in respect to what, this x and y, they should be constant. Okay. That's a very common mistake when you do this first step. A lot of students actually use 0, 0 at here. That's seemingly to be a minor difference or mistake at the beginning. But trust me, because next you're going to do integration using the line integral, and that essentially will give you completely different results, okay, for the next few steps. So make sure that you got this right first. Okay. Now that's another example in terms of the parametric equation in here. And I'll give you another one here. This is not a parameter, but this is just to kind of show you what Okay, so this last example is not to parameterize a certain curve. Is you were given a parametric equation already at here. And let's see if you can trying to visualize what kind of curve this parametric equation represents in 3D space. X of t equal to a cosine t, y of t equal to a sine t, and z of t equal to bt. So let's focus on x of t, y of t first. Okay. If I just look at x of t, y of t, a sine, a cosine, a sine, and what kind of curve does it represent? Circle, right? Okay, good. So basically, if I change the t starting from 0, in this particular case, if I change the t from 0 to 2 pi, it goes along a circle and come back to its original location, right? It's 360 degrees. Now let's put in the z of a t into the picture. Now you should try to imagine now as t changes, the z is also changes, which basically going up, right? So as t goes from 0 to 2 pi, the z goes from 0 to 2 pi b. In other words, you imagine you're going along the circle, but then at the same time you're also going up, right? You're also going up here. So altogether, this will generate a so-called a spiral curve or helix, basically. Okay, so that's how this looks like for this type of curve. If I plug in a specific a and a b value, so that's called a helix. It's a very useful actually curve, and you have seen this kind of things. It's a spring, basically, right? You've seen the spring profile like this. If you pick a screw, okay, if you look at the threads of the screw, that's exactly also a helical profile. And if you look at this particular equation, as I mentioned, as t changes for one term, and the z value, right, in this particular case, it goes up by 2 pi b, right, in this case here. So basically when t goes from 0 to 2 pi, this is one term. then the z goes from basically 2 pi b in z direction. Okay. That's the nature of the curve, the helix curve right here. Now this 2 pi b right here, we have a name, it's called the pitch. Okay. So basically, if you look at the thread profile of a screw, and if you starting from one point and you move one turn, right, it goes back. It didn't go back to itself. It goes right somewhere on top of it. But then there's this distance, right, between the two adjacent points. That's called a pitch. That's a thread, basically. Right? So you can change A, B value, and you'll get essentially here. You see the demonstration here. A is all 5, 5, and then I guess in this here I changed the frequency T. Instead of TT, the second drawing is 2T, 2T. So you see basically a denser type of spring now, right? Rather than this one. Okay. So that's how you can manipulate this helical spring here. In mechanical engineering, when I teach the helical type of a gear, the gear profile, the helical gear profile, okay, is also part of the basically just a segment of this helical curve. Okay, that's a helical type of gear. And in this week tutorial, you have a question and tutorial on the spur gear, and that profile on the spur gear, okay, is also a parametric equation that you will see that how it can be derived. Okay, it's a very useful representation now. So I'll show you another example here, very interesting ones here. You can actually construct quite interesting curves using parametric equations. So, for example, right? Let's see, we have a parametric equation x equal to sine theta e to the power of cosine theta minus 2 times 4 theta sine Alright, so I'll give you a parametric equation. Okay? It's not in the parameter t, but it's a theta, which is fine. Okay? Yeah. So you look at this one here as well. What exactly does that represent? There's so many cosine, sine, exponential. Right? It's just insane. But if you plot it out, basically, for example, you treat theta as a t, okay? And when you plot it out, and you get this. Okay? It's a butterfly, right? It's insane. So there are many other situations like this. Okay? I can show you actually really a different kind of that's the beauty behind the math here, right? Yeah. And when we learn surfaces, okay, and we'll see actually there are many other different examples. Okay. So I will encourage you to plot this using MATLAB in the assignments. I sometimes give you some sample codes or using Maple or MATLAB. So you can try plotting all of this. You can even construct your own parametric equation. Right? You can see this. What if I times another sine theta here? Then what does it become? Right? So you can really construct your own parametric equation and come up with an insane different type of curves. Okay. All right. So that's enough for parameterization of curves. Let's move on to a different topic now, which is actually not so different, okay? But it really, we call it vector function. Okay, vector function here. It's a new topic, but once you see what I'm writing in here, it's really nothing new. We have seen it all, basically. Okay? Let's put on the formal definition first. So if I have a curve in 3D space, okay, so here's a curve C. As I mentioned, to represent this curve, I can represent the curve using parametric equation. Basically, we derive a set of equations: x of t, y of t, z of t, x of t. And then x of t, y of t, z of t itself, they are essentially representing the coordinates for any points on the curve, right? So x of t, y of t, and z of t. Okay. So if I connect the origin with that particular point, okay, represented by these coordinates, okay, then mathematically I establish a position vector that represents the position. This vector represents the position of this particular point. So I will use r of t, okay, to represent this position vector. The reason we have bracketed t is because the p is a moving point. As time changes, as the parameter t value changes, then this vector r of t will also change. That make sense? So this r of t, which is a position vector, and basically here is what we're talking about, the vector function, right? It's a vector, and it's also a function. It's a function of t. So there's nothing new here, right? So basically this r of t, okay, is called a vector function. And for function, mathematically what it means is you have a parameter, okay, and you plug in this parameter or the variable with a different value. So in this case t is a parameter. When you plug in this t with a different value, you get a different return. Okay. And then this return right here is a vector. So you plug in a different t value, you will return a different vectors. And that vector right here in this particular is a position vector. So that's why it's called a vector function right here. So t, there's always a range for the t. Okay? When you define a function, there's always a range of t. It could be from negative infinite to positive infinite. But when you plug in a value into that function, it needs to return certain values. That's the ideal function right here. Now, if I coming back to all the parametric equations, you look at all the parametric equations right here, everything that all the different type of parametric we have derived. Basically, I can always write, okay, all the parametric equation into a simple short format using this vector function concept. So all I need is I can just simply write like this. Okay. And the x, t, y of t, z of t, that's however the results is. You can plug it here, or different notation wise, we write it as this. Okay, so different notation. That's the expression wise. That's how you express a vector function. Good. So for example, for a line, right? Okay, for a line, you can write down the line equation as typically as it is. Like this is how we write our line parametric equation. Separately, three equations. Now, I could use now vector function to represent this line equation. So this side here, okay, that's our r of t, and this one here is a constant position vector. Here's a coefficient t, and then here is the parallel vector. So altogether, I could write it just r of t equal to a constant position vector plus the coefficients times the parallel vector. So you can see now the three equations can be very briefly, right, very neatly written down as one single expression. Now this is a vector function. Okay. Yeah. So as you can see, even though this is a new concept, but it basically is based on whatever that we have learned about the parametric representation of a curve in 3D space. So, and the next few points is, if this is a function, well, in more specifically it's a vector function, then I really wanted to apply everything that, all the calculus that we have learned regarding a typical function to this vector function. So, calculus for a typical scalar function, meaning you do derivative, you do integrals, right? So we wanted to do exactly the same thing. How do I do integrals for this vector function? How do I do derivatives for this vector function? So this is basically the next few, until the end of this lecture, we'll look at derivatives and integrals for vector function. Okay? Yeah. As you're going to see, talking about derivative and the integrals, it's the same idea, and you actually will see much similarities when you do derivative and integrals for a scalar function. Okay. So maybe I should emphasize vector function. So make sure there's a difference here versus the scalar function. Okay. And of course it's different because scalar function, when you plug in a t, you will get back a scalar value. In the vector function, when you plug in a t, you get back a vector. Right? That's a fundamental difference. So let's look at the derivative. Okay. Derivative vector function. And I will follow pretty much exactly the same kind of notation-wise, and also same kind of concept, okay, for a derivative of a scalar function. Okay. So let's say I have a curve theta here, and it's at this point, okay. So here is one particular point, r of t, and then here is another point at here. Suppose it travels, okay, along this direction at here. At t moment, this is a current location. Then after delta t time duration, we end up at this location, so that's t plus delta t. So after a delta t duration, we're end up at here. Okay. Then apparently, I can construct another vector, okay, between these 2 points. So you have initial displacement, and then you have the final position vector, like here. So the difference between these two, right, give us the so-called difference, delta r. Right, so now if you think about the scalar function, we do the similar thing, right? You have initial at x, that t moment, and then end up at t plus delta t. Then there's the difference between this function, the value, right, between this f of t plus delta t and the f of t. So now talking about derivative now basically means if I'm gonna do this operation here, okay, I will use the final position vector minus initial position vector. So r of t plus delta t minus r of t, use this position vector minus this, we get the delta r here, right? That's your delta r. Okay, so this part here is your delta r, the top. Or maybe I'll write it down here. So delta r equal to r t plus delta t minus r of t. Good? So delta r is a differential position vector. Okay. And then I will divide this whole chunk by the duration of delta t. Okay. So this is essentially like the rate of change, right? The rate of change of this position vector here. And now for derivative basically means we will let the delta t go to 0. Okay, approach 0. Take a limit. The results of this is a derivative. And then you can define the derivative now. Okay, just like a scalar function. So dr of t over dt, right? This vector here, that's the derivative. Okay. Now, of course, I skipped some very rigorous writing in here. Not necessarily derivative always exists. You know, it's just like scalar function. When you take a derivative function at a certain point, it probably doesn't exist. Okay. If it doesn't exist, basically means it's not differentiable at that point. Okay. Yeah. And the same concept also applies. And not necessarily the derivative vector function always exists. If it exists between a certain range for the t, it means it's differentiable. Okay, during that in that range. Okay. But in short, that's your derivative definition for vector function. Alternative writing for derivative, okay, is r vector prime of t. Okay, so sometimes you also see this kind of right notation in my lecture notes or in the class. Okay. And by the way, this is the Newton type of notation. Okay. And I forgot what this type of notation is for column. Okay. So when it comes to specific calculation, right? Let's see if I give you an example now. Okay, so here is an example of vector function. And I want to calculate what is dr over dt. Okay, so before we do the calculation in here, let's look at this given parametric equation of vector function. 3 cosine, 3 sine, and then t squared. So what does that remind you? What type of curve are we talking about here? It's a spiral, isn't it, right? But it's not the kind of spiral I was given, because the t here, the z here is what? It's a z t squared. So instead of evenly going up, t squared basically means exactly, right? You know, the spring is actually it's nonlinear, spread out as t going out. Okay. Now, when it comes to the calculation derivative for this vector function, it's actually quite straightforward. All you need to do is you calculate the derivative of each one of the components. Okay, each one of the components here. And when you calculate the derivative of each one of the components, and that has no difference from the derivative of a scalar function anymore. That's basically what you learn in your first year. If you look at each one of the function here, and in this case it's very simple. Derivative of 3 cosine t is negative 3 sine t. 3 sine t here, 3 cosine t. T squared 2t. Okay. That's the results. So even though we're talking about derivative vector function, ultimately what we're doing is derivative of scalar functions here, right? Each one of these. Okay, very straightforward. Now, second of all, okay, and I still wanted to not just a derivative concept, right? I still want to relate to physics, a physical concept here. So if I take if the R of t here represents its a position in scalar sense, if let's say if a scalar function represents displacement, then when you take a derivative, what do you get? You get not velocity, you get the actual more precise description is speed, right? You get a speed. So if R of t here represents a position vector, then when I take a derivative, so technically speaking, we get, what do we call this? Velocity vector here. Right? We get velocity vector. So when you take a derivative of vector function, which represents a position vector, then its derivative gives you the velocity. Okay. And velocity vector, as we're going to show you here, so basically this is the position, velocity. Velocity vector is also always a vector parallel to, not parallel, a tangent to the curve. Okay. Tangent to the curve, the point is moving. Okay? Yeah. So what if I'm going to take another derivative based on these results, or basically means I'm going to take a derivative of this velocity vector here. So let's call this as v at here. Okay. So we're going to take one more derivative. So physically, what type of vector we're getting at here? Acceleration, exactly. Right. So acceleration vector. Now, when we write this notation here, okay, I can write it like this. Okay. I can write it like this. So here's the original velocity vector, and here's d over dt. That's basically another operator, another derivative operator here operating on this. Or you could just simply say this is the second order of derivative. Then the calculation-wise, no difference from the previous one. You do the derivative for each one of the component, okay? And I will end up with -3 cosine t, 3 sine t, and then finally 2. That's acceleration vector. Okay? Yeah. So, and then there are a couple other properties associated with the vector functions. For example, like product rules. Okay, this is the very basic rules that you use for scalar function derivative. Same rule actually will also apply to vector functions. So I'll list a couple of these in here. Okay, and you will see. It's nothing different from a scalar function. So let's say I've give you two vector function. Okay, so giving u of t and v of t. Now we can have a product rule. So let's say we're taking derivative of u of t dot v of t. U of t dot v of t. Just be careful. You cannot just simply multiply two vectors, right? You're not multiplying two scalar values. When multiplication for vectors basically means either dot product or cross product. Okay, so you cannot have just simple multiplication, right, of a vector function. So you could dot product or cross product. Okay, that's multiplication. What multiplication means for vector functions. Now, product rule, you get exactly the same kind of a writing like a scalar function here. So du over dt over dt times v of t times means dot right here, and then u of t dot dv of t over dt. Okay. Now cross product, no difference, basically just a cross at here. Okay. A simple product rule applying to vector multiplications. Okay, and sometimes you can also, this chain rule also comes in handy. So suppose I'm taking the derivative of a vector function u, and u is a function of x, and then x is a function of t. So that's product, that's chain rule right here. So u is a function of x, and x is a function of t. So chain rule basically means you take the derivative of u with respect to the x first, and then multiply by the dx times dt. Okay. Yeah. So this is a pretty straightforward. I don't think we need really any exercise here. If you're given u of t, v of t, and the rest of things are very straightforward calculations like what we did here. All you need is just derivative of each of the components of the vector here, right? Yeah. Let's take a look at the slightly different example here, because I think we're going to need this one here for the future exercise. So this is more of just a demonstration, okay, rather than a question in here. Let's say we have a vector function. It's a special kind of vector function. It has a constant length. Okay. Vector function with a constant length. First of all, it's called a vector function, but fundamentally, it's basically what? It's a vector. Right? It's a vector. If this is a vector of a constant length, so direction I don't care. So if I vector here is r of t, then basically means its length is a constant. It may point into different direction, but every time at a different t, it's always the same magnitude, same length. So then what's so special about this kind of a vector then, right? So let's take a look at this particular one here, okay? Let's take a look at this particular. As a matter of fact, I can give you an example, okay, of a certain trajectory that end up with a vector basically function of a constant length. So if this is an xy plane, if I'm going to draw a circle, let's say not necessarily a unit circle, let's say I have a circle in the xy plane with a radius of a, okay, with a radius a here. As we learned, if I want to represent that particular circle, I can use parameterization, and I can actually use a position vector here, r of t, okay, to represent any point, right? To present any point moving along that circle. So if you look at this particular one here, let's say you started here and moving around here, and r of t, a candidate of r of t, as we learned before, could be a cosine t, a sine t, right? That's your r of t possible solution. Now if you look at this one, what's the length of this r of t? It's a. which is a constant length at here, right? Constant length. So that's the kind of a situation I'm talking about here. What do we mean by a vector function of a constant length? Okay. So as a matter of fact, this is basically the kind of a motion, you know, it's circular motion, right? It's a circular motion around a circle. Okay. So now I'm going to do some operations at here, okay, to show you, given such a type of vector function, what's the relationship between the position vector and its velocity vector, okay, or its derivative. Okay. So, for example, here, if it's moving along the circle here, as you learn in dynamics, let's see if it's moving at a constant velocity or angular speed at here, then what is that position? What is that velocity vector? Velocity vector, you draw what? You draw it over here, right? Velocity vector, okay? Yeah, which is tangent to the circle at here, and the position vector is here, right, for that particular point. Now, if you look at the drawing I showed you at here, here's the position vector, here is the tangent vector. So the way I showed you here, the position vector and the velocity vector, they must be, what's the geometric relationship? They must be what? Perpendicular, right? That's what we learn in dynamics. But why? Can we prove that? Right. So let's show why this V and R, they're perpendicular to each other based on this simple relationship. So here's how we're going to prove it. Using the definition of dot product. If you recall that, okay, if I use a vector dot itself, when I use a vector dot itself, what am I supposed to get? Not a 1, not 0. R squared, which is meaning, well, why don't you write it out here? Let's see if R equal to A, B, C, for example, right? Okay. So what's the dot product? The results. What does that mean? A squared plus B squared plus A squared. This is basically what? Huh? What's the length of this? What's the length of the vector? Right? So then the dot product of the vector itself give you exactly. Right. It gives you the square of its length. Right. Square of its length here. Okay. All right. So according to my notation, is a c square at here, right? Now this is a very simple fact I really want you to remember. The dot product, the vector itself, give you the length squared. Okay, so now from here I'm going to do a manipulation of both sides of this equation now. So I'm going to take a derivative of both sides of this expression. So that's legitimate because I'm not changing anything, I'm just taking derivative of both sides. So that equality here still maintains. Then, but what's good is this side is a constant, right? And then the constant derivative must be 0. And the other side, inside the bracket, essentially are two vector functions. So I could use the rule which I have just said. Which rule? The product rule here. If I apply the product rule here to the left side, you get dr of t over dt dot r of t plus r of t dot dr of t over dt. Right? Just treat it as if there are two vector functions inside bracket. But dot products are commutative, so a dot b equal to b dot a. That's called commutative. So now you look at these two terms, they're basically the same, right? So that gives you 2 times r of t dot dr of t over dt equal to 0. And you can cancel the 2 out because the other side is 0. So you end up with just simple expression r of t, the vector function, dot its derivative, which is velocity, equal to 0. So now it seems clear now. When you have 2 vectors, dot product 0, meaning the 2 vectors must be perpendicular. And that shows the proof here. The position vector is perpendicular to the velocity vector. Okay. Any questions so far regarding derivatives? Yes?
I think I missed one point. The reason we know that the derivative is 0 is because it's constant. That's correct.
You mean this one?
On the right side of the equation.
Here?
Yeah.
Yes.
Okay.
C squared is 0, so when you take a derivative of a constant with respect to anything, or t, right, it's 0.
Okay.
Yeah. Okay. So that's about derivatives. So let's take a look at integration. Okay, let's look at integration, or integrals of vector function. Given a vector function r of t, and if we're going to integrate both sides of this integral of this vector function, it's very straightforward. All you need to do is you do the integral for each one of the component. Okay, so you do the integration of each one of the components at here. And if you look at the results at here, so you get a scalar function here, scalar function here, scalar function here, but when you put things back together, you get essentially again a vector function. Okay? So you're going to get a different vector function in here. However, remember, you don't stop at here actually, because this is an indefinite integral. Okay, so when you integrate, for example, when you integrate a scalar function, you get its antiderivative, and remember what you do next? You plus a c, right? Constant c. But here, what do? Do we plus a constant c? A vector, so a constant vector c. Okay, excellent. It's the same idea as the derivative. If you take the derivative r of t plus this constant c, you get this constant c with respect to t0, right? Yeah, that's antiderivative r of t here. This is the formula basically for integration. This is indefinite, right? This is indefinite. If it's a definite, if it's a c 0 to 1 or something, then you don't need a c anymore. Okay. Yeah. Okay, really, in terms of exercise, there isn't much to exercise here. It's just the typical integrals that you have done for your first year, right? So why don't we just quickly give a quick example here: 2t negative 1, 3t squared. So suppose this is your r of t here, And if we're going to integrate this particular one, okay, so we're integrating is, okay, so here's typically you can write it like this, just like we can write it like this. So -2t, -1, 3t squared, and then dt. Right? You can even write it just like that. Okay. So integration meaning integral of each one of these. Okay. We get the first one is t squared equals t and t cubed. Okay. And then don't forget plus a constant c. Very straightforward. But that's what it means for integral of a vector function. Okay. Okay. And essentially, that's all about calculus for not all about the simple, derivative integrals for vector functions that are here. But I do want to mention a couple important ones that are here, especially. Actually, a couple of them we already covered here. So, tangent vector, unit tangent, and then unit normal. Okay, so I'll explain what this means that are here. So let's start with a curve C. And I'm going to pick point on the curve C. For that particular point, it's a position vector. If this is a general point on the curve C, I can use a general vector function r of t to represent the position or to represent the curve C. Okay? And as we learned previously, if I take the derivative of this position vector r of t, so what we essentially get is we get the velocity. Right? We get the velocity here. And the velocity is always tangent to the trajectory the point is moving along. So this v of t here must be tangent to c. So this v of t is tangent to c, curve C. So this actually brings us, instead of I call it the velocity now, I'm going to call this dr over dt, I'm going to call it a tangent vector to the curve C. Okay. So we define a tangent vector t, which is dr over dt. Okay? Yeah. So nothing new here, right? It's just a different name calling. Okay. And then from here, I'm going to normalize this tangent vector or to derive the unit tangent vector. And that's also very straightforward. All you need to do is unit tangent vector is you divide it by its length, okay, then you get the unit tangent vector. Is that good? Okay. So nothing new in here. But now I'm going to introduce a new concept now. Okay. So let's see if this is my curve at here. Okay, this is curve C. Okay. Here's the curve C. And here is here is the tangent, unit tangent vector t at here. Okay, so here is the unit tangent vector t. Now, if I move along the curve, let's say the next time over here now. Okay, so after a certain amount of time, so let's say for example this is at the t moment. Okay, at the t moment it's here. If we move it a little bit more delta t duration, then this unit tangent vector will come over here now. So this is t plus delta t. Make sense, right? Okay. So then I'm going to apply, okay, the derivative concept as we learned at the beginning. I'm going to use this t hat, okay, t plus delta t minus t hat delta t hat t. Okay. So use this vector minus this vector here. Okay, right. So basically it's like this. So here's one vector t hat t, and here is the vector t hat t plus delta t. Right. So vectors free, right? So you can always move them to start the same location. Then when I use this one minus this, I get this vector here. This is like delta t hat. And then divided by delta t. And let delta t go to 0. So that's a derivative concept, right? That's derivative concept. And this derivative concept here will yield basically dt hat over dt. Okay? Give you this derivative dt hat over dt. So as you can see here, right? As you can see here, that new vector here, this new vector dt hat over dt. So basically it's going to be a vector pointing somewhere in this direction given by the delta t hat. Okay? Yeah. Now that direction, right, if you think about it as delta t go to 0, that direction, okay, basically is a direction pointing to a direction where the curve is turning. Can you see that? Right? So if your delta t becomes really small, delta small duration t become very small, and that delta t hat basically, or this dt hat over dt will be a point, will be a direction pointing to where the curve is turning. Right? If you this one here, you have another direction here, turning here, right? So this guy here give you the direction of turning of the curve. Okay? Give you the direction of turning of the curve at here. It's a very important direction. Okay? So because when you drive a car and you know the velocity, you also want to know which direction you're turning here, right? So that direction is given by dt hat over dt. Then what is the relationship between dt hat over dt and then t hat then? So you have t hat, you have a dt hat over dt. What is the relationship between these two? Perpendicular. Excellent. Because we have shown you when you have a vector function of constant length, then its derivative is perpendicular to itself. And now we're talking about as a t hat, right? We're talking about t hat here. T hat is unit vector, which guaranteed to be a constant length. So that means these two dot product is 0 or perpendicular. Okay, so perpendicular here. So you have t hats over here, and you have a dt hat over here, right? which is perpendicular to each other. T hat is unit vector. Then I'm going to define dt hat over dt as the so-called normal vector. Okay, and here. Now, you have to be very careful. T hat is a unit vector, but that doesn't mean that the dt hat over dt is also a unit vector. So that's why I just called it a normal vector. I didn't call it a unit normal vector here. Alright? So if I want to obtain unit normal vector, what do? We just normalize again to this normal vector to get a unit normal vector. It basically means you're normalizing dt over dt hat over dt and then divided by its length. Okay. I think symbol kind of a little bit build up at here now. Okay, but it's still the same idea of the derivatives. So, in short, okay, here's a couple of things I want you to remember. We're going to exercise here. 3 expressions. What's tangent vector? What's unit tangent vector? And what is normal vector? And what is the unit normal vector? Okay, yeah. So 4 formulas at here. Okay. Finally, there's another vector here. Is to get a cross product between the unit tangent and the unit normal. The result that here is a unit vector. This is basically called a binormal vector. So when you cross producting 2 unit vector, and you get back unit vector. So that's a rule here. And this is called a binormal vector. So it's like this, right? So you have a t hat over here, and then you have n hat, which is perpendicular between these two, and then you get a b hat, okay, after the cross product. So if I show you this, what do you think this will remind you of? So 3 unit vectors, right? 3 unit vectors here. What do you think that reminds you of here?
Coordinate system.
Exactly, a coordinate system. In our case, it's I hat, j hat, and k hat, right? Coordinate system here. Excellent. Okay, so I do have an example here, so we still have a few minutes. I don't think I'm able to finish example, but let's just start example here. Okay. Here's the vector function, and I want you to obtain the unit tangent vector and the unit normal vector. Okay. So this part of the exercise here is not really about the concept anymore, because you will see the concept is very straightforward. You know, it won't take you more than a minute to remember what unit tangent or unit normal vectors are. But you will see that the exercise, actually the focus here, is all about a computation of a derivative now. Okay, so this seemingly to be a very simple vector function, but once you calculate the derivative of a couple iterations like this here, things kind of becoming a little bit complicated here. Okay, so let's start a question here. To get the t hat, and I need to know the tangent vector first. And tangent vector is just a simple derivative of the vector function r, and that gives us 2t g hat 3 not g I 2t I hat 3g hat and then plus 0, right? Because this is 5 here. Okay. That's pretty straightforward. And then I'll calculate the unit tangent, which is the normalized version of that. So divided by the length. And here is the original t, so I need to divide it by length. And the length is 4t squared plus 9 square root, right? So 4t squared plus 9 square root divided by its length. And then 2t at here plus 3g hat at here. Okay. Good. So we finished one, which is the t hat. Okay, we got it. Okay. And then now I need to obtain n hat, right? So n hat. But in order to get n hat, and I had to get dt hat over dt first. Okay, the unit tangent vector's derivative. So this is the part things a little bit complicated. Okay. So dt hat over dt first. This gives us the normal vector, right? This gives us the normal vector here. So what's confusing to some student now is because the t hat has a 1 over root 4t plus 9. That may make things a little bit more messy, but this is still a typical derivative kind of question. So when you take the derivative of this dt hat, you're basically taking the derivative of each one of the components here, right? So essentially you're taking derivative of the first one here, which is 2t over 4t squared plus 9. That's the first term. And then you're taking derivative of the second term. Okay. That's what you do. So I want you, I don't think this is new. I want you to review now, just make sure to get ready for the midterm. What is the derivative like this kind of a function? How do you compute the derivative function? Because I know for facts in the past, a lot of people having trouble calculating derivative like this kind of thing, right? You can either use product rule, or you can either use, what's the other rule? Quotient rule, right? So it really doesn't matter. Quotient rule, and I get questions, a lot of time get questions by student, can you write down the formula for quotient rule? If I'm happy, I'll write it down for you, but otherwise I won't. Okay, so I think that's very basic ones. You need to be able to memorize these rules that are here. That's the quotient rule, right? Yeah. So I don't have time to finish this now, but I want you to, this kind of thing, as I emphasize, you need to be able to calculate these kind of derivatives, all right? And I'll finish this in the next lecture. Okay. Any questions? Good.